Hi, I am Peter Karpov. I am a PhD student at Mises. As an undergrad, I studied quantum physics not that long ago, and I clearly remember how tough it can be. So I'll try my best to help you to master the world of quantum. In the previous episode, we discussed the waves of matter. In this episode, we'll extend this wave picture and introduce the so-called wave function, or psi function. In classical mechanics, state of a particle, say an electron, at a given time instance, is described by its position r and momentum p in 3 dimensions, or by x coordinate and p in 1 dimension. In classical mechanics, we can, at least in principle, find out where the particle is and also in which direction and how fast it moves. But quantum mechanics tells us that particle cannot possess some definite coordinate and definite momentum simultaneously. This is called the Heisenberg uncertainty principle. We'll discuss it in more detail in the next episodes. On the other hand, quantum mechanics tells us that particles actually behave like waves. This means that we have to invent some new description of the particle's state. And this new description is the concept of wave function, psi of r in 3 dimensions, or just psi of x in 1 dimension. For simplicity, we will work mostly with this one-dimensional case, at least in the beginning. In this case, psi is a complex function. It maps the line of real numbers to the complex plane. So the natural question arises: what is wave function, and which kind of wave it describes? The question was, and still is, debated one. We'll stick to the so-called Copenhagen interpretation. It states that particle's position is undetermined until it's being measured, and that psi function is related to the probability of finding particle at point x at the time of measurement. Let's consider an example. Let me have a particle living on a line and having some wave function psi of x. The physical meaning of psi function is that psi of x modulus squared delta x gives the probability that particle has a coordinate in range from x to x plus delta x for small x. When coordinate of the particle is being measured, it's most likely to be found near the maxima of wave function. It may seem peculiar to write modulus and square simultaneously, but remember that psi of x is a complex function. So, like for any complex number z equals to x plus iy, where x and y are reals, the modulus of z is the distance from the origin, and it is given by this. Introducing the complex conjugate, we can also write it in this way. So, z modulus squared equals to z times z complex conjugate. Since psi of x modulus squared delta x gives us a probability, then psi of x modulus squared itself is a probability density. If we divide the line in some small segments, x1, x2, and so on, we see that this sum gives us the probability that the particle is present somewhere on the line. It is just equal to 1. Transferring to the continuous limit, delta x goes to 0, we immediately see that the sum transfers to a definite integral. This is called the normalization condition for the wave function. Now we can ask, in what units the wave function is expressed? The answer depends on the dimensionality of the system and can be easily deduced from the normalization condition. For 1D system, we see that the right-hand side is dimensionless. dx has the dimensions of length, therefore psi modulus squared has dimensionality of length to the power minus 1. So the dimensionality of psi itself is length to the power minus 1/2. From the same reasoning we've got the normalization condition, we get that the probability that the particle is present between some points A and B is given by the same kind of integral, where the integration goes from a to b. Now let's consider an example. Let a particle on a line has the following wave function. So the wave function is non-zero on the segment from minus L to L and is zero outside it. Note that this function is continuous, as psi function should always be. So the first task is to find the normalization constant R. Now let's consider an example. Let a particle on a line has the following wave function. First, let's guess the form of the solution. From the dimensional analysis, we see that since psi is proportional to L to the power minus 1/2, then A have to be proportional to L to the power minus 3/2. Now we want to find the precise expression for A. Let's utilize the normalization condition. Here, psi modulo squared equals psi times psi conjugate. In order to take complex conjugate, as a rule of thumb, we just substitute I by minus I. So here is our psi complex conjugate. And note the minus sign here in the exponent. Since psi is equal to 0 outside the segment from minus L to L, then the integral's limits also reduce to minus L and L. So we write the normalization, substitute psi and psi star, and these guys are cancelled. Since the integrand is even, we can write the integral from minus L to L as twice of the integral from 0 to L. Performing the integration, after some simple algebra, we obtain this. So we obtain our normalization constant A. We see that our initial guess that A is proportional to L to the minus 3/2 was correct. A constant phase factor like minus 1 here, or generally some e to the power I5, does not influence the physical probabilities, so we choose the plus sign here. Finally, we get psi of x. Note that the factor e to the power ix cannot be omitted, since it's not a constant, it varies with rank x. In conclusion, in this episode, we have discussed the wave function and its physical interpretation. Psi of x modulo squared gives the probability density of finding the particle at point x. Integrating the probability density over the whole space, we get the probability of finding the particle somewhere in the space, which is 1. This is called the normalization condition. In the next episode, we'll discuss observable quantities and the corresponding quantum mechanical operators.